The Chesterton 4400 Twin Hybrid Gas Seal, In-Gland Control System. The Chesterton in-gland control system regulates barrier gas pressure within the seal itself, without external pressure regulators. The IGCS uses a diaphragm mechanism to detect changes in the process pressure. The movement of the diaphragm controls an internal valve that regulates how much barrier gas is supplied to the faces, so that the pressure differential between process and barrier can be maintained. In this 3D animation of the 4400 seal, fluid pressure levels are indicated by colors, from blue, green, yellow to red in order of increasing pressure. The IGCS cavity to the left of the diaphragm is filled with the process fluid, which passes through a filter disc and enters via the process reference port. The pressure from the process fluid acts on the surface area of the left side of the diaphragm, creating a force. An additional force is created by the differential screw and bias spring located on the left side. This adjustable spring force creates the differential between process and barrier fluid pressures and is factory calibrated to provide an additional pressure of 20 psi. The barrier gas pressure on the right side of the diaphragm creates a force working to the left. When the diaphragm is in the middle neutral position, the barrier gas pressure force is equal to the process pressure force plus the adjustable spring force. Since the forces on either side of the diaphragm are working on the same surface area, this means that the barrier gas pressure at the diaphragm and the faces is 20 psi greater than the process pressure. The fluid colors indicate this relationship. The yellow barrier gas pressure is higher than the green process pressure. When the process pressure increases, shown by the color change from green to yellow, this increasing force results in an axial displacement of the diaphragm to the right, which causes the actuator stem to force the ball off of its seat. The ball seat pairing is actually a valve. By displacing the ball from the seat, the valve is opened. Barrier gas at feed pressure flows around the actuator stem into the chamber to the right of the diaphragm and all the way down to the faces. With the valve open, the barrier gas pressure increases on the right side, shown by the color change to orange, so the diaphragm moves to the left. When the barrier gas pressure force is equal to the process pressure force plus the spring force, the diaphragm returns to a neutral, undisplaced position. The ball reseats, closing the gas feed valve. At this point, the barrier gas pressure at the diaphragm and the faces is once again 20 psi greater than the process pressure. By adjusting the differential pressure screw, the spring or bias force is increased or decreased, meaning the differential pressure the seal will operate at will be increased or decreased. During operation, as process pressure climbs or the seal uses gas at the faces, the IGCS adds gas to the faces to maintain a steady differential pressure. As process pressure drops and pressure on the right side of the diaphragm must be relieved to maintain differential, volumes in the gas flow porting are so small that this relief is provided almost instantaneously via the gas consumption at the faces during operation. Since the barrier gas feed pressure area is isolated from the faces by the ball seat valve, barrier gas can be brought into the seal gland at pressures up to 350 psig for applications of 300 psig or less, and the IGCS will track process pressure to the set differential. The in-gland control system workstation. This workstation demonstrates how the in-gland control system maintains the differential between process and barrier gas pressures when the process pressure changes. The operator can change the process pressure and observe how the barrier gas pressure reacts. The 4400 seal is installed onto a shaft in an acrylic chamber. Water is the process fluid and filtered air is the barrier gas. Two temperatures are monitored. The seal face temperature is measured by a thin wire thermocouple that is glued to the stationary face at the ID. The process temperature is measured by a thermocouple in the chamber. The barrier gas and process pressures are also monitored. This transducer measures the process fluid pressure. The other measures the barrier gas pressure delivered to the faces. A pressure regulator controls the process fluid pressure. By bringing the process pressure up and down, the operator can simulate the pressure changes of typical operating conditions. The barrier gas filtration and monitoring unit for the 4400 supplies a sufficient quantity of filtered gas to the barrier gas port. It does not regulate the pressure, as control panels for other gas seals must. The system consists of a bypass switch, bypass line, coarse and fine filters, check valves, and optional flow meter. During normal operation, the gas passes through the coarse and fine filters, which eliminate any moisture and debris that might damage the seal faces. The bypass valve and line allow the operator to change a filter without shutting down the gas supply to the seal. When it's time to change a filter, the operator turns the switch to bypass so that the gas goes through the bypass line directly to the barrier gas port. The check valve keeps the gas from flowing back to the filters. When the changeout is completed, he turns the bypass switch off and the gas now goes through the filters. Demonstration of pressure regulation. In this demonstration, the adjusting screw of the 4400 seal has been set for a pressure differential of 20 psig. The barrier gas pressure will be 20 psig greater than the process pressure at all times. The motor is turned on. The process pressure is adjusted to 30 psig. Notice that the barrier gas pressure is 52 psig, about 20 psig greater. The pressure regulator is turned to increase the process pressure by 5 psig to 35 psig. Now the barrier gas pressure increases to 55 psig. The process pressure is increased another 5 psig to 40 psig. The in-gland control system brings the barrier gas pressure up to 59 psig, maintaining the 20 psig differential. When the process pressure is quickly dropped from 40 to 25 psig, the barrier gas pressure also drops the same amount, from 60 to 45 psig. Rapidly increasing the process pressure back up to 40 psig causes the in-gland control system to bring the barrier gas pressure back up to 60 psig, still maintaining the 20 psig differential. The in-gland control system, the 4400 seal, ensures that when the process pressure changes, the barrier gas pressure also changes to keep the correct pressure differential for optimum sealing. More reliable, less costly, easier to maintain. The in-gland control system of the Chesterton 4400 twin hybrid gas seal is a significant improvement over the static pressure regulators used by other gas seal designs.